Okay, we pick the second half of this lesson up when we want to calculate internodal distance. So, here's your formula for calculating internodal distance. Give me a little bit of a legend to work with here. Um, Basically, you're just looking at half lambda, where for a standing wave, where does that node occur? So if we have a standing wave here, sketch it off to the side, it's not overly shocking where the formula comes from, because if this is your wavelength lambda and your crests and troughs don't move, guess what? Your node is in the middle, so it's half of lambda. So I know it's absolutely shocking, the formula, but that's really all that's involved. So distance between nodes, distance between nodes. That makes sense too, because your node's also going to occur here, because this is the next part of the wave, and here, that's the next part of the wave, and so on and so forth. And lambda is your wavelength, of course. So there you go. So taking a look at an example here. This is a standing wave. So as soon as you see the word standing wave, you know you're dealing with nodes that aren't moving. So it occurs in a duck pond when a duck repeatedly tries to jump for food. So it's going up and down, creating a standing wave. If there are nodes at every 38 centimeters, so basically if I'm decoding this, I know my internodal distance is 38 centimeters, which I'm going to convert to meters. What wavelength of wave is the duck creating? So lambda is the unknown. Well, this particular formula, there's only two unknowns, so it's not too hard to figure this out. So 38 equals 1/2 lambda. So lambda will equal 0.76 meters. So therefore the wavelength is 0.76 centimeters. Sorry, meters. Wavelength is 0.76 meters. So B part, if the wave speed in the pond, so now I'm given the speed of a wave, so it's a velocity, how often is the duck jumping? Well, basically what this is asking is, what's the frequency that the duck is bobbing up and down? So we're just going to use our universal wave equation, which I said would come up over and over and over again, which it has. We're looking for frequency, and I now know my wavelength to be 0.76. Doing some calculations there, I find my frequency is 1.25 hertz. So this means the duck is jumping every 1.25 seconds. So therefore, the duck is jumping every 1.25 seconds. There we are. So that's using that internodal distance. That's for standing wave, calculating wavelength and so on and so forth. So let's talk about resonance for a second here. So resonance, every object is vibrating at a particular frequency, and some objects we call this the natural frequency. So I have to do both physics term and a music term because people know it as a little bit different. So basically, it's just going to create a table here. So in terms of frequency, I'm just going to go with F, 2F, and 3F. All right, just to give you whatever the frequency is. Now for the diagram, for the first frequency, it's basically, looks like this, the wave. All right. The physics term for this, we call this the first harmonic. For the music people in here, you're going to call this the fundamental. Fundamental. For our second natural frequency, what would happen, it'd be in the same length, except we have a nodal point. Okay, so it's that same lambda, where I'm trying to draw the same length of wavelength, but this time we get an extra nodal point in there. All right, the first wave there is the most basic wave that I can get between point A and point B. Okay, now I can get to point A to point B by adding a crest and a trough. So physics people, or physicists, try not to be too adventurous here. We call that the second harmonic, whereas music people will know this as the first overtone. The third frequency then, so if I want to go from point A to B again, and adding an extra nodal point in there to go to 4 nodal points. So you see the pattern, 2 nodal points, 3 nodal points, 4. All right, maybe I'll just highlight that. So here's, got 2, then I've gone to 3, then I've gone to 4. Okay. Physicists continue with the pattern, third harmonic, and the musicians, same thing now at this point, they go to the second overtone. So anyway, to finish off this particular section then, so basically what's happening here, resonance occurs when a standing wave is created. Standing wave is created at a multiple of the natural frequency. And that's what we're talking about above here in that diagram. I'm talking about this being the first natural frequency, all right? And here's a multiple of that natural frequency and a multiple of the initial frequency. So we're just looking at multiples of that natural frequency. So resonance, that's when you get vibration. If you have something, for example, if you play an instrument and the window starts shaking, you might be playing at that resonance of the window, and it's what we call the natural frequency, the natural, what that particular object wants to vibrate at. All right, so as we move on then, mechanical resonance is the vibrating response of an object to a periodic force from a source that has the same frequency as the natural frequency of the object. So the example is the tuning forks. Now you've done the tuning forks hopefully demonstration in class here already with the previous kind of a lab or investigation. But what happens is if I have tuning fork number 1 here, so draw a crude tuning fork here, where you strike it and vibrates, so it creates its sound waves. So step 1, strike the tuning fork. Then a second identical tuning fork over here. Okay. So you strike this one with the hammer. It creates the vibration. Sends the waves out. Okay. The second tuning fork. Will begin to vibrate. And again, something you should have already seen if you've done the demo or the lab. It's something that you should have expected. And there we are. Also, if you want to, there's a second video there, a YouTube video, talks about the Tacoma Narrows Bridge. And what happens with the Tacoma Narrows Bridge, if you go ahead and watch the video, it's a very big bridge that actually collapsed. So it was across a gorge, and what happened was the wind, when the bridge was finished, the wind, when it came down that sort of valley at 42, and it was 42 miles per hour, in American, what happened was the cross-section of the bridge, it reached its natural frequency, so the bridge started to, or the roadway, so this is a cross-section of the roadway, it started to started to vibrate because it's its natural frequency at that low wind velocity. So here is the center of the road. This is where the yellow line would be. And it would start flexing just like that. So as you'll see in the video, the road starts to vibrate, or the bridge starts to twist and vibrate to the point where it critically fails and absolutely crashes. And that's because it reached that wind caused that natural frequency to occur. Of the bridge. So the video is pretty neat to see if you haven't already seen it. So make sure you take a look at it first, or right now if you want to pause this and take a look at that actual disaster. So a couple of less disastrous examples of resonance, and that's talking about rocking a car when stuck in the snow, pushing a child on a swing. So each of those requires you're amplifying, you're building up the supercrest and super trough. So what I'm going to do, I'm going to come back, I'm going to finish this lesson in the next one, just so I'm not rushing to get everything in, because I want to talk about a couple things here, and then you're all set to go in the next section here.